In our last three examples, we want to continue looking at data to construct polynomial models. Rather than power functions though, now we're going to look at, for instance in example 5, constructing a quadratic model. When we start to see this language, we need to identify or mentally identify the type of equation that we're trying to generate. A quadratic formula or quadratic function would be something of the form ax squared plus bx plus c. So when we use Desmos to construct this model, we'll need to input something of that form. In this case, we're told in part A to treat age as the independent variable, meaning that age will be our x variable and that percentage p will be translated into our y variable. Flipping over to Desmos, we can start constructing a new table. And I'm going to pause to get my data entered, and we'll continue from there. Once we have our data entered and we know the type of model that we want to construct, simply a matter of typing y1 and then using that tilde symbol, and then entering something of that general form that we're after. So we have ax squared plus bx plus c, where we're using x1s and y1s to make sure we're referencing those columns. And Desmos is going to output those values for a, b, and c for us. Those results in this case tell us that our model of best fit would be y equals 0.016 x squared minus 1.465x plus 42.98. In part C, we're asked to predict the percentage of 55-year-olds that don't have a high school diploma. This would correspond to plugging x equals 55 into that model we've just constructed, which would give us a value of approximately 10.8%. Example 6 is similar, though now we're going to be asked to construct a cubic model. A cubic model would be something of the form ax cubed plus bx squared plus cx plus d. So cubic referencing that our highest power is 3, or that the degree of that polynomial is 3. We want to let x equals 0 represent the year 1900, which means each of these values are going to be updated when we put them in the Desmos. And so on for that second column. We always want to look, if we're dealing with years, to see if we're given some specific 0 year. And then we'll switch over to Desmos to input that data and get this process started. I'm going to pause again while I input that data, and then we'll pick back up with constructing that model. Once we have our data input, we can construct our model by entering y1 and that tilde symbol, and then constructing the right form for the model that we're interested in constructing. Again, Desmos will output those different values for us for each of those coefficients. As sort of a trick here, sometimes Desmos won't always output all of the decimal places that we want for our answer. So what we can do is, in some additional cells, type in each of those letters that correspond to those coefficients, and we'll get those decimal places carried out farther so that we can match the rounding that we might be asked for in a given homework problem or exam problem. So for example, d equals 13.634 is really a much longer repeating decimal answer. This means we've found a model that, with our coefficients rounded to 5 decimal places, would be 0.00015 x cubed minus 0.03039 x squared plus 1.60142x plus 13.63395. we want to find all extrema for this data, meaning we can switch back to Desmos until we can see our complete scatter plot and our curve, and find that we have a maximum occurring at 35.557 and a minimum occurring at 101.71. So we'll round that to 35.6 comma 38.8 was our local maximum, and our local minimum was occurring at 101.7 comma 17.4. So if we're looking specifically on this interval from 20 to 130, that means that in 1935, so x equals 35 would correspond to approximately 1935 or 1936, depending on how we rounded. We had the highest rate of elderly men in the workforce. And that in x equals 101.7, so either 2001 or 2002, we had the lowest rate of elderly men in the workforce. Neither of these values are absolute maximums or minimums, but again, since we're given the interval to look between x equals 20 and x equals 130, between those intervals we are taking on our highest and lowest values, even though they aren't the overall highest and lowest values if we consider the full domain of the function.